Hello and welcome to the section 4.1 lecture. Today we're going to start looking at representing linear non-proportional relationships. A lot of stuff going on there, a lot of big words. I get it. We talked last module about proportional relationships, which meant two things. It meant that it was a straight line and it went through the origin. So technically, to get non-proportional, you just have to fail one of those two things, or both. It could be something that's not a straight line and doesn't go through the origin. That would be non-proportional. You could have something that that isn't a straight line, but still went through the origin. That would still be non-proportional because it's not a straight line, so it doesn't meet that one of those criteria. But what we're really restricting ourselves to are the linear non-proportional relationships. Basically, all that means it's a straight line that doesn't go through the origin. So that's why I said that the tables, the graphs, the equations, all those things, the idea of slope is not going to go away. We're still going to be using slope here. Let's go ahead and take a look at it. Representing linear relationships using tables. Okay, in this example, it says that the equation y equals 3x plus 2 gives the total charge y for one person to rent a pair of shoes and bowl X games at the Baxter bowling lanes, blah, 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 based on the prices shown. Okay, choose several values that make sense in the context. So number of games. We probably don't want to consider a negative number of games. Okay, and really even 0 games, you're not going to go there and get shoes if you're going to bowl 0 games. You're just not going to. And so we pick the numbers. This example picks the numbers 1, 2, 3, and 4. And then we use the equation and plug in these values of x into this equation. So each one of these involves the math that it takes to go 3 times 1 plus 2. They tell you right there that it's 5. This one takes, let me actually move it over here, 3 times 2 plus 2. 3 times 2 is 6, plus 2 is 8. 3 times 3 is 9, plus 2 is 11. 3 times 4 is 12, plus 2 is 14. And this is a great, I love that they put this poster on here because this is where that equation comes from. It's a $2 shoe rental. You don't pay for the shoes every game you bowl. You just pay for the shoes once and you have them until you return them. And then it's $3 for every game that you bowl. That is how you get that formula. It says here, Francisco makes $12 per hour doing part-time work on Saturdays. He spends $4 on transportation to and from work. So we get that equation, y equals 12x minus 4, where y gives us his earnings after transportation costs, and x gives the number of hours that he worked. So make a table of values for this situation. Again, it's letting us pick the x values, and then we have to find the y values. Okay, the x values don't really matter, but we can go and look at, there are things that make sense and there are things that don't. He's working on a Saturday. How many hours do you think he's going to work on a Saturday? Probably not 40, because there's not 40 hours on a Saturday. Let's say he works, 2 hours, 4 hours, 6 hours, and 8 hours. And we can figure out how much he makes from that. So if he works 2 hours, this piece right here, I'm actually going to try to fit it in here. It might be a little bit tough, but we're going to see what we can do. To find out why, it's going to be 12 times 2 minus 4. 12 times 2 is 24, minus 4 is 20. This one would be 12 times 4 minus 4. 12 times 4 is 48, minus 4 is 44. 12 times 6 minus 4. 12 times 6 is 72, minus 4 is 68. And lastly, we have 12 times 8 minus 4. 12 times 8 is 96. minus 4 is 92. Okay, so if he works 8 hours, he gets $92. Pretty cool. If he only works 2 hours, he only gets $20. Okay. So let's check out this activity here. It's about examining linear relationships. It says, just to read that prompt up at the top, it does say, recall that a proportional relationship between two quantities in which the ratio of one to the other is constant, blah, blah, blah. Okay, let's look at this instead. It says the entrance fee for Mountain World theme park is $20. Visitors purchase additional $2 tickets for rides, games, and food. So the equation y equals 2x plus 20 talks about the total cost y after purchasing x tickets. Okay, so the 20 here is from the $20 entry fee, and you're going to pay that whether you play any games or ride any rides or eat anything. You're going to pay that $20. And then, depending on how many tickets you buy, if you buy X tickets, that's going to increase your cost. Okay? So we complete the table. Again, if you don't ride any rides, you don't buy any tickets, it still costs you $20 to get in. For this one, we would think about 2 times 2 plus 20. 2 times 2 is 4. Plus 20 is 24. Next one is 2 times 4 plus 20. 2 times 4 is 8 plus 20 is 28. Maybe you can start to see a pattern. 32, 36. Did I do that right? Yeah, I did. Plot the ordered pairs on the from the table and describe the shape of the graph. At 0, costs us $20. Each line is worth, it looks like 4 here. 4, 8, 12, 16, 20. 2 tickets costs us $24, so I'll get it 2.24. 4 tickets costs us $28. 4 tickets, 28. And then 6 tickets, 32, and 8 tickets, 36. So we get a straight line right here. And that should kind of give us the idea of the shape of the graph. It's a straight line. The only thing that's different from what hey, God, it doesn't really look that straight, does it? Do the best you can. The only thing that looks different from between this and what we did before was that it's not going through the origin. Find the rate of change between one point, between each point and the next. Is the rate constant? Okay, every single time. So what this is trying to get us to do is to find the slope. Okay, on the graph, it's showing that it goes up 1 and over 2 every time. Okay, scale-wise, that's not what that means. But on the graph, it's going up 1 and over 2. That really means a $4 increase for 2 tickets. So you would kind of say that it's actually like up 4 and over 2, or a slope of 2. Okay, if we're using what we did before. Now again, on the graph, it's showing go up 1 line and over 2 lines, but because of the scale that they have this graph set at. But it is a constant rate of change. Yes, it's constant. And what this rate is saying is that the cost is $2 per ticket, which, believe it or not, we already knew. Okay. Calculate y over x values in the table. Explain why the relationship between the number of tickets and the total cost is not proportional. Sorry, that went down the wrong pipe. Sorry about that, but I'm okay. Well, whenever we try to calculate y over x in a problem like this, we're in trouble right off the bat. First one I have is 20 over 0. That's undefined, right? That doesn't work for us. The next one I have is 24 over 2. Sorry. Which is 12. Okay, and those two aren't the same. So right there we know it's not proportional. I can keep going though. I get 28 over 4, which is 7. Still not the same. Gosh, what are we getting at here? That's kind of the question. This is 5 point something. But, I mean, it's not 6. It's not 5. It's somewhere between 5 and 6. And the last one would be 36 over 8. And that would equal 4 point something. Okay. So it's not proportional because the rates of change are different. Because y over x is not constant. All right, let's look at these questions down here. Analyze relationships. Would it make sense to add more points to the graph from x equals 0 to x equals 10? Would it make more sense to connect the points with a line? I mean, no. If they're talking about this problem, would it make sense to add more points to the graph from x equals 0 to x equals 10? I mean, you could, right? You could figure out how much it would cost you total if you found, or if you bought 5 tickets or 7 tickets. But we're probably not going to buy a fractional amount of tickets, so there's only so much that you can do. But yes, you could. I'm just going to say you could find the cost of 5 tickets. It would just give you more data points, which when you're graphing lines, the more points that you have, the easier this is to graph. So what I didn't really show you, I mean, I graphed all those. It really only takes 2 points to give yourself a line. So I could have done it with this point, and I could have drawn a line. But as I start to draw my line, it could start to veer off one way or another just slightly, but enough to make a difference. So the more points I have, now the trick with these points is they would have been somewhere in between grid lines, right? So maybe that's what they want us to get at. But yeah, they would just be between grid lines. But still, the more points I have, I think the easier it is to draw a straight line. Gosh, that makes it kind of easy. And then I always notice when I run out of points, I'm like, oh, where do I go? So the more points you have, the easier it is. Would it make sense to connect the points with the line? Explain. I'm going to say yes and no. For the reason that, and maybe I'll just say no. Maybe it's not that good to say yes and no. It's nice to know what 5 tickets would cost, and maybe they didn't even want us to draw that line. Maybe that's what they were getting at there. Yeah, not really. They just wanted us to plot the ordered pairs. So maybe I'll get rid of that line. If you already drew the line, that's okay too. It's relatively okay to draw that line. So we have these ones. And so all they're really getting at is that, and I'm just going to go ahead and say no, that would it make sense to connect the points of the line? No, for the simple fact you can't buy let's say 4.5 tickets. And that's what they're getting at here, is that if you were going to draw a line, it would be that idea of a continuous thing, that you could get any of these values. On problems like this, you should just leave it as points. But, I mean, lines are pretty. Lines look good. When we get lines, we get good things happen. Okay, so we got one more thing going on here. Talking about linear equations. Everything with linear equations comes down to the formula, or the what we call slope-intercept form of a linear equation of y equals mx plus b. Okay, and then when b is not equal to 0, that relationship between x and y is non-proportional. Okay, let's look at this second example. The diameter of a Douglas fir tree is currently 10 inches when measured at chest height. Over the next 50 years, the diameter is expected to increase by 2/5 of an inch per year. So we get the equation y equals 2/5 x plus 10, because that's the 10 inches that it's at right now, and then the 2/5 that it's supposed to grow. It gives us this table. It is non-proportional because it doesn't go through the origin, but it does give us a straight line. Okay? It does give us a straight line. So let's look at how we can do that. Okay, one of the easiest ways to draw your straight line is to come up with some points. And for the most part, it doesn't matter what your points are. See, I was better that time. We want to make a table and graph the solutions of the equation. So I'm going to plug these values in. They picked points for me, which is kind of sad, but it works. -2 times -1 is +2, plus 1 is 3. -2 times 0 is 0, plus 1 is 1. -2 times 1 is -2, plus 1 is -1. You can write all these out if you want to. -2 times 2 is -4, plus 1 is -3. So graphing these, I get this one just gives me the point -1, 3. This gives me the point 0, 1. This gives me 1, -1. And this gives me 2, -3. -1, 3. 0, 1. 1, -1. And 2, -3. I'm going to go ahead and I don't like to call it cheating. I like to call it using my resources to give myself a straight line. I don't draw straight lines that way very well on this tablet. Okay? And that's it for today. So the last thing that we need a code word for the day. And we're going to go with something a little bit silly, just because. We're going to go with Douglas. I like Douglas. I like Doug fir trees. Your code word for today is Douglas. Okay? All right. Have a good day. We'll see you in class.